All right, guys, in this lesson we're going to be looking at confidence intervals for the difference in population means. So we have been looking at population proportion. For this part of the chapter, we're going to be looking at population mean. So our objective here is just to describe the center shape and spread of a sampling distribution. We also want to determine the conditions for inference for the difference of means, as well as construct and interpret a confidence interval to compare two means as well. So let's think about sampling distributions first. We know that when we are asked to describe a sampling distribution, we're asked to describe the center, spread, and shape of this. So we need to basically figure out the difference between the two means. We need to figure out the standard deviation of the difference of those two means, and then we also need to understand what the shape is actually going to be. And we need to be able to describe all of that. So in this example, we're asked to explore the sampling distribution of bar x of 1 minus bar x of 2. Let's start with two normally distributed populations having known means and standard deviations. Based on the information from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls follow a normal distribution with a mean of 56.4 inches and a standard deviation of 2.7 inches. The heights of 10-year-old boys follow a normal distribution with means of 55.7 inches and a standard deviation of 3.8 inches. Suppose we take an independent simple random sample of 12 girls and 8 boys of this age and measure their heights. What can we say about the difference between the two means in the average heights of the sample of girls and the sample of boys? So first we need to describe the actual shape itself. So if we're given the shape, which A is representative of the sample mean of the girls' heights and B is representative of the sample mean of the boys' heights, you'll notice that both are very, very normally distributed. So if both are very normally distributed, then we can assume that the difference between the two are also going to be normally distributed as well. So that's the only thing really to note, is that if you are given two normally distributed populations and they say that both of them are normal, which they're both normal in the example, then we can assume that the difference is also going to be normal as well. Again, we need to find our values of interest. So once we have discerned that the two sampling distributions are approximately normal, we need to then find the center and spread. And our center is essentially just going to be the means that they give us, and the spreads are going to be the standard deviations. Now, they give us our standard deviation of 2.7 from this sample and 3.8 from this sample. We need to find the standard deviation that's representative of the entire population. So we need to find the standard error, essentially. And that's going to be taking the standard deviation of the girls divided by the square root of the number of girls in the sample, as well as the standard deviation for the boys divided by the square root of the total number of boys in the sample as well. And then we also need to understand that 12 is probably going to be less than 10% of the population, and 8 is going to be less than 10% of the population as well. And then finally, once we have found those critical values, we need to compare those two. And so in order to find the difference of means, all we really need to do is subtract the means. So we would subtract the mean height for the girls minus the mean height for the boys, and we get a subtracted mean height of 0.7. And then for the difference in standard deviations, we must add their variance. And so we must take the standard deviation that we're given squared divided by the total number of girls, and then the standard deviation for the boys squared divided by the total number of boys as well. And we need to add those two. That represents the variance for each. We need to add those two variances together and then take the square root of that, which gives us a standard deviation for the difference in means of 1.55. So again, when we are describing a distribution, we need to describe the shape. So when the population distributions are normal, the sampling distribution of x1 minus x2 is also normal. In other cases, the sampling distribution of x1 minus x2 will be approximately normal if the sample sizes are large enough. So we can also discern if we're given a large enough sample and they don't tell us that both of those distributions are normal. Again, we can use that central limit theorem where as long as both samples are greater than or equal to 30, then we can assume that both distributions are normal. So therefore, the difference in distributions is also going to be normal as well. Our center is just going to be the mean of the sampling distribution, which again, all we need to do is subtract both means to find the difference in means. And then our spread is going to be finding the difference in standard deviations, basically, or the standard deviation of the difference in means, which is going to be denoted by that example that we just saw. And this is as long as each sample is no more than 10% of its population. So that also needs to be checked as well. All right, so let's look at an example of how we might solve this. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with mean 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution with a mean of 17 ounces and a standard deviation of 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of the 20 cups filled with the large setting and 25 cups filled with the medium setting. We want to let the mean of L minus the mean of N be the difference in the sample mean amount of liquid under the two settings. So for part A, we're asked to describe what is the shape of the sampling distribution at the mean of L minus the mean of M and why. Well, we know that the mean of L, or L in general, follows a normal distribution. We also know that M follows a normal distribution as well, so it's safe to say that the shape of the sampling distribution is going to be normal since both population distributions are known to be normal. Part B asks us to find the mean of the sampling distribution and show our work. All we need to do is subtract the means from the mean of L minus the mean of M, and we get the difference in means of 10 in this case. So our mean difference is 10 ounces in this case. And that's our center. And our spread is to find the standard deviation of the sampling distribution and show our work, which again is just adding the two variances and taking the square root of that. So we're given a standard deviation for L at 0.8 and a standard deviation of M at 0.5. So we would take 0.8 squared divided by the total number that's in L, or in the L sample, plus 0.5 squared divided by the total number that's in the M sample. Take the square root of that, and that gives us a standard deviation of 0.205. And since the population is theoretically infinite, the 10% condition is met in this case. So that's essentially how we describe a sampling distribution for a difference in means. Now, we also have conditions that need to be checked, which, again, this should come as no shock because we've been going over this forever now. So, again, before we get into intervals, we have to make sure that we check three conditions. The sample has to be random, it has to be independent, so the sample size has to be less than 10% of the total population, and it has to be a normally distributed sample, or a large sample, one or the other. So they either have to say that both samples are normal. If they don't, then you want to check to see if the sample size, both sample sizes are large enough. It's very, very important that both sample sizes be greater than or equal to 30. You can't just have one sample size that's greater than or equal to 30. If that's the case, then the central limit theorem applies. Otherwise, you have to graph the data in order to determine whether or not it is a normal distribution. Okay, from there, we can determine our test statistic. So since we often do not know the population parameters when testing for a mean, we will continue to use a t distribution instead of z to figure out our test statistic. So that's just going to be the sample of 1 minus the sample mean of 2 minus the population mean of 1 minus the population mean of 2 divided by our standard error right here. And again, the denominator is the standard error of the sampling distribution. So the sampling distribution, not the population distribution, because we don't know the population distribution, or we don't know the population standard deviation. And again, if you are ever asked on any question to determine what the standard error is, then make sure you are just using this formula that's in the denominator to tell what that standard error is. Now, when we looked at just a one sample trying to find the mean for one sample, basically. We also had this idea of degrees of freedom. In this case, we are going to use our calculator to calculate the degrees of freedom for a two-sample t-statistic, because the formula for the degrees of freedom is no longer just n minus 1. It is this nice little thing right here. And so I would highly suggest not trying to figure out the degrees of freedom this nice long way, because the odds of entering something in wrong on the calculator are pretty astronomical at this point. So I will show you a way in just a second of how to find that on the calculator. But we need to know that a two-sample t interval for a difference between two means, so when the conditions are met, an approximate confidence level for a confidence interval for our mean 1 minus mean 2 is going to represent this formula right here. So this is just the basic formula where we take the difference between the two means plus or minus our test statistic times the square root, excuse me, not the square root, the standard deviation of the difference between two means. So here t star is our critical value with its confidence level of its area of negative t and t for the t distribution, with degrees of freedom using either option 1 on technology or option 2, the smaller of n1 minus 1 and n1 minus 2. All that's to note is that I'm going to show you how to find the critical value. So let's take a look at how we can solve for confidence intervals, or the full way that we need to solve for confidence intervals. So the Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height in centimeters. Here are comparative box plots of the data and summary statistics from Minitab. So we have our northern trees that number about 30 in the total sample. They have a mean diameter of 23.7 centimeters and a standard deviation of 17.5, with our southern trees that number about 30 as well, with a mean diameter of 34.53 centimeters and a standard deviation of 14.26. So how we're going to solve for this is just by going over to stat and tests right here. And then you want to arrow on down to 0 or just press 0 on your calculator, and that should take you to two-sample t-int. And again, we're using t, or two-sample t-int, because we are working with two samples. We want to use t because we're trying to find the confidence interval for a mean, and the interval is what we're trying to find. So if you arrow over to stats, once you are on that, for our southern trees, they had a mean of 34.53, so we want to enter that in. For our mean 1, our standard deviation 1, they also had a standard deviation of 14.26, and there were 30 total southern trees in the sample. Our northern trees had a mean of 23.7 with a standard deviation of 17.5, and they had 30 total trees in the sample. From there, we want to enter in our confidence level. So if we're trying to find something at a 90% confidence level, which they don't tell us in this problem, but let's say that we're trying to find something at a 90% confidence level. This is not a pooled interval, so we don't need to worry about that. And then from there, we can calculate. So once we calculate, we should get our interval right here. This is how you would find the degrees of freedom right there, so super simple. And then they give you the rest of the information that you pretty much input already. And that's essentially how you will find our confidence interval for a difference in means. So that's not all that we have to include, though. So again, when we're looking at confidence intervals, we have to go through the 4-step process. So you have to state the parameter, which in this case the parameter is the mean difference in dBH of the northern versus southern halves of the longleaf pine trees. Okay, we are told from there, we have to plan. So we have to check all 3 of our conditions to make sure that they that they meet our criteria. So we're told that the samples are random. We can assume that there are at least 300 trees in both halves of the preserve, so 30 is going to be less than 10% of the total number of trees that represent the population in both halves of the preserve, the northern and the southern half. So the samples are independent, and since both are large or at 30, right at 30, the central limit theorem will ensure that the sampling distribution is approximately normal. So it can equal 30, and the central limit theorem still apply. From there, we need to complete the do portion. So we need to run a 2-sample t interval, which is what I just showed you how to do, for the difference in population mean, which again, that gives us a confidence interval of 3.93 to 17.72. So that's the difference between the two means. And then if we were running a confidence interval for a 90% confidence level, we would conclude by saying that we are 90% confident that the true mean difference in dBH of the northern and southern halves of the Wade Tract Preserve is between 3.9 and 17.7 inches. So this suggests that the northern trees are definitely larger than the southern trees.